Now we will moving on to the next session. Of course, one of the interesting sessions from our undergraduate student team from IIC. So they have done a small project on LLM, and then they are so excited about. Yeah, now we can introduce them.
Okay. So up next we have something very special So at CASML we truly believe that a conference should be more than regular talks and technical sessions, and it should also be a platform where young researchers can shine and show their work. So based on that, we have some young researchers from IIC undergraduates who want to showcase their work called MentorX. It's a student-led initiative from IIC, and I would like to invite the MentorX student team to the stage and take the stage forward.
Good afternoon, everyone. Today we present MentorX, an AI tutoring framework designed to transform large language models from answer generators into true educators. So we are entering an era where AI is being rapidly integrated into STEM education. So current state-of-the-art models answer questions instantly, but answering is not teaching. So studies show that current LLMs can hallucinate facts, offer generic explanations, and encourage shortcuts over learning. So what happens is that students risk shallow learning and over-rely on AI tools, while parents lose trust in digital learning tools that promise growth but deliver shortcuts. So we introduce MentorX that is built around the LMT square framework, which is learn, master, teach, tuning paradigm. The model first acquires domain knowledge, then masters its application through feedback-driven practice, and finally teaches using an adaptive Socratic style of instruction. So in short, our vision is to build an AI teacher that can learn like a student, reflect like a researcher, and teach like a professor. So before we dive into the MentorX framework, it's important to understand why such a system is needed. So today when students turn to LLMs for help, the mode of learning changes. So instead of exploring, reasoning, and struggling productively, they receive answers instantly. And the moment that happens, the learning shifts from active effort to passive consumption. The thinking stops, the answer becomes the focus, and the reasoning behind it is often skipped. So this creates a surface level grasp of concepts. The students see the solution, but they do not internalize the underlying logic. So the model hallucinates or presents information without proper grounding of facts. Learners may unknowingly observe inaccuracies. And because the interaction feels smooth and helpful, they may develop an illusion of understanding, even when comprehension is shallow. So as usage continues, reliance increases. Over time, students begin to trust outputs without question. So they fact check less, they engage less critically, and revise less. The role shifts from a problem solver to an answer consumer. So the metacognitive awareness, that is understanding how they think and learn, weakens because the cognitive struggle is now outsourced to the AI model. So with repeated exposure, these misconceptions can solidify and bias can creep into the student's mental model. Since the AI model is generating reasoning for them, the brain exerts less effort. So the learner stays within a comfort zone of quick answers rather than developing resilience through exploration and failure. And what this reflects in? This reflects in the academic outcome. So what happens is that creativity declines and there's an over-reliance on AI tools. So motivation drops because an answer is just a single prompt away. So it becomes easier to ask than to think. So in short, LLMs are powerful tools, but without structure, feedback, and pedagogy, they can unintentionally erode core learning skills. MentorX exists to address this gap. Now over to Shashank to explain the first part of the framework.
So the first part of the framework is knowledge gap assessment plus teaching material curation. In this part, we will assess the model's capabilities on what it knows and what it doesn't know. But before directly asking a question on the uploaded document, what we do is we generate a strategic plan on how to ask questions, and we generate a score which is dependent on relevance, accuracy, as well as completeness of that particular topic in that document we upload. Then we generate a knowledge graph, which is an edge-weighted one, wherein the edge weights denote the closeness between two topics. If two topics are highly correlated, then their edge weight is close to 1, and the other way around. Then we generate multiple choice questions based on Bloom's taxonomy. That is, per topic we will be having at least 6 number of questions, and then for the options we we generate options in such a way that those options will be distracting the student. And then we pass this quiz to the student LLM, which we train in the next phases to become a teacher. And based on the number of questions it answers correctly and the number of questions it answers incorrectly, we then generate a data set which covers up both the correct as well as incorrect topics in the proportion we set, as well as the difficulty. So all these steps are iteratively refined such that there is a critique LLM as well as a refiner LLM, wherein the critique LLM critiques the decision generated by the teacher LLM, as well as the refiner LLM, which refines the output based on the critique LLM. This data set is passed to the further modules. Over to Akanksha.
So coming to the next part of the stage 1, that is the learning stage, we have the learning from the teacher, that too in a structured aware manner. So, so in our prototype that we have built, we focused on K-12 math. So our goal is to build a CBSE math specialized model. So here we are taking a student model, that is the Llama 3.18 billion. So we are basically fine-tuning it in a structured manner using the data set that we have obtained from the previous models. So we are using prompt KD and struct tuning methods. Like we are gonna format the data, each sample of the data set into a particular prompt, in which even we involve the knowledge graph thing, and we get the output as the merged LFT fine-tuned model. Yeah. So we have tested this model on, we have taken a quiz on the base model as well as the LFT fine-tuned model, and there's an improvement in the accuracy as well. Like it started giving more number of correct answers compared to the base model, and we also have the text similarity metrics to align with the teacher's chain of thought reasoning. Now, in the learning from teacher module, what it lacks is that it lacks in the interaction with the teacher, direct interaction. So to improve that, there is one more thing done, that is the interactive concept refinement, where the student model is given a chance to interact with the teacher in turns. And yeah, so this is the pipeline of that. So the student model, basically what it asks, the main motto is that we need to correct the chain of thought reasoning of the student model. So it asks doubts related to the questions it has incorrectly answered in each chapter. Then we have the teacher feedback, which is the Kimi K2 model, and teacher refines the student's chain of thought reasoning. That is basically what we do in the concept refinement. And after that, we take the trajectories and we generate a data set based on that using the backward construction method, and we use LoRa to fine tune the model with that particular data set. So we have obtained around 500 questions overall. So on that, the model showed a performance of around 3% improvement from the LFT fine-tune model to the LFT plus interactive concept refinement model. So we also test the text similarity metrics like blow score and ROW and meteor score. So yeah, over to Ashwin.
Great. Now that we have covered how students learn concepts, clear doubts, and refine their understanding, we move into the feedback-driven practice stage of the student-teacher lifecycle. So in a classroom, students learn a concept from the teacher and then apply it through assignments, quizzes, or problem solving. So they receive feedback, correct mistakes, and progressively tackle harder problems. So this feedback loop is what truly strengthens the understanding. LLMs, however, naturally don't get this benefit. So most models are trained on static data sets, but these alone are not sufficient for true mastery or for deep reasoning. So humans can learn from limited examples and still generalize well because of the feedback loop that is happening. So to bring this behavior into models, we introduce a dual agent framework to enable feedback-driven practice. So our approach operates on a progressive, basic, generalized, harder loop. So the cycle begins by the student tackling the problem in the original data set. The teacher reinforces the problem-solving skills of the student by introducing conceptually similar problems. that then finally the teacher enhances the student's learning by introducing incrementally harder problems. So once this is done, this is followed by an iterative refinement loop where the student updates his responses based on the teacher's feedback. The cycle continues until the teacher deems the answer to be satisfactory, allowing the student to gradually improve to targeted correction. Finally, all the synthetic data collected is then used for model training, where we improve the likelihood of the student response being accurate and the efficiency of incorporating the teacher's feedback back into the student. But just like in real learning, one teacher alone is rarely enough, which brings us to the next stage of the framework. So cumulative learning experience. So quite often a student may not fully grasp a concept by learning from a single professor alone. They explore external resources like another lecturer, a YouTube explanation, a textbook, or a paper discussion. So each teacher introduces a slightly new perspective, and this diversity in instruction often leads to deeper understanding, new insights, and sometimes even novel ways of thinking. So we can apply a similar idea to LLMs. If a student model only learns from a single teacher model, it risks inheriting the teacher's limitation and inductive biases. So we extend our framework into a multi-teacher knowledge distillation where the same student LLM undergoes the feedback-driven practice loop which happened before with different teacher models. So now that we understand why multiple teachers improve learning, let's look at how we actually integrate them into a training pipeline. So rather than relying on one teaching data set, we generate several data sets from multiple teachers. We then fine-tune the base model on each data set using LoRa, which gives us multiple student checkpoints. So we then sample prompt checkpoint pairs, which acts as supervision signals for training the parameter generator. So the objective here is to help the parameter generator learn how to produce task-specific LoRa waves dynamically based on the input prompt. So now that we have generated multiple student checkpoints, the next challenge is bringing them together. And that's where the stage 2 comes in. So in step 1, we compute a task vector for each LoRa. So what do we do? So we take a base model and its corresponding LoRa adapter. So we give both the same input and we ask the model and we extract the final layer embeddings. So the element-wise difference is the task vector. In step 2, we use a variational autoencoder. The encoder projects both the LoRa embedding and the task vector into a common latent space, and this is KL divergence regularized in order to make it smooth and well behaved. Finally, in step 3, we sample a latent representation and pass it through the decoder to reconstruct a conflict-free multi-teacher aware LoRa vector. Now it's over to Shobnik to explain the post-instructional reflection.
Yeah, so now that our model got cumulative learning experience, our last steps towards increasing the model's accuracy is self-reflection. So why self-reflection? Recent work shows that LLMs can improve their reasoning by analyzing their response and refining their response and trying to improve its capability of giving correct answers. So we use this framework latent evolve, where we don't have to fine-tune a bigger model, but we can fine-tune a small model so that it can improve the accuracy of the bigger model. So this framework is inspired by how humans learn. So in the daytime, we try to gain as much experience, or we try to learn as many things as possible. And in the nighttime, when we sleep, we process all this information into our memory and we keep it in our long-term memory. So the core idea is LLM improve its answer during inference by involving latent representation over multiple iterations. So it has two cycles. In the daytime, we retrieve the latent trajectories of the model's answering capabilities, and in the nighttime, we train a small latent viewer model where we use those extracted latent embeddings to train the small language model. So why it's powerful? We can use this framework without fine-tuning the large model, and it can generalize across various tasks. So in the phase 1, what we do is we maintain one episodic buffer memory where we have context, that is the query which is being given to the language model. we maintain the base chain of thoughts which model generates initially and the evolved chain of thoughts which model generates after the self-refinement, which is the second step. So the model evaluates its own reasoning patch to guide the optimization. So we use RLVR, which is reinforcement learning for verifiable rewards, where we ask model whether the solution provided by the model is in correct format or not, is it correct or not, is the methodology explained in a correct way or not. So we extract the correct chain of thoughts which leads to correct answers, and we save them in one episodic buffer memory. Then we use that episodic buffer memory and we train a small language model, which is the latent weaver model, and we fine tune this small model based on those extracted latent embeddings. And while inferring, we pass the query to small model. It generates some initial chain of thoughts, and we pass that initial chain of thoughts to the bigger model so that it can get initial good start. So this framework improves the accuracy in the inference time. Then now we'll move towards the learning by teaching module, where teacher model, like our model learns how to teach in a better way. Over to my teammate Mehul. Thanks.
Yes, so moving forward in our training framework, classically when we talk about knowledge distillation, we think of a bigger teacher model transferring his knowledge to a weak student. You can think of it as a one-way process. The knowledge flows from teacher to student. This particular idea flips this paradigm. Inspired by Feynman technique, we try to gain a deeper understanding of a topic by teaching it to someone, here another LLM. Building on previous slides, LFT paradigms are usually unidirectional. LBT, learning by teaching, introduces a bidirectional feedback loop. So it turns the training into a conversation rather than a lecture. Failure of the student model becomes feedback for us, guiding the teacher model to improve. So before diving to the full pipeline, here's the idea on how we will go about engineering this new paradigm. So there will be a teacher model which will explain a problem. The student model will solve a similar problem using that explanation. If the student model is not able to solve, the explanation was insufficient and the critic model will come into play. On the good and bad explanation, we can use a DPO to train the teacher model. So idea is to create a closed loop in which the model can autonomously improve its training data by itself. Here's our whole pipeline in our setup. The teacher and student model are Llama 3.18 billion. The critic model is GPT-OS is 20 billion. As you can see in the diagram, the teacher model is connected with an external data source. It will generate teaching rationale and teaching answers, and the student will attempt an exam problem using the material given by the teacher. So each sample will give us a teaching rationale, teaching answer, and the student model will give us the exam rationale and exam answer. In the second diagram, you can see each sample's TR, TA, ER, and EA are evaluated and combined into an LVT score. The LVT score is a weighted combination of TA and EA. The correctness of TA and EA we can find from the external data source. We have used symbolic math libraries from Python and LLM as a judge to verify the correctness of the answers. The high scoring TAs will become positive examples and low scoring will become the negative examples. Unlike the standard fine tuning, which only keeps the good samples, here in DPO, we can leverage both the good and bad rationals. So this prepares us for our next module, Pedagogy RL, in which the teacher will try to become better at teaching by using Socratic ways of teaching.
So now we'll be coming into the final stages of our project. So till now, our model knows how to solve problems really well, and all that's left is to fine tune it to teach better in a Socratic style. So what we want from an ideal tutor is to avoid answer leakage, use Socratic questioning, provide scaffolding, and then promote long-term learning. So why do we need to fine tune? Why not just use prompt engineering? So the problem with prompt engineering is if you just say behave like a Socratic teacher and then refrain from giving answers, well, there's always scope for jailbreaking it. And students might spend most of their time jailbreaking it into getting the answer rather than solving the problem on their own. So prompt engineering is gone. SFT, it's really hard to generate the data. It's expensive. Same as the case with RLHF. So in our case, we'll be using GRPO. So basically, we need a teacher that is able to solve the problem on its own internally, which is already done, and we need some pedagogical alignment. So it must be able to communicate that knowledge as helpful stepwise guidance without leaking the final answer. So yeah, so the teacher model is the Llama 8 billion, which was got from the previous modules. The student will be the 7 billion Quen 2.5, and the judge will be the Quen 14 billion model. So the student and the teacher is made to simulate a multi-turn conversation. And for each question answer pair, we make the student and the teacher talk for 8 times. So after talking for 8 times, for each conversation, we find a reward. After finding the reward, then we use straightforward GRPO to update the teacher's weights. So this is just the breakdown of the reward function. Well, there's no time, so I won't go into it. Let's just see a demo. So we'll be simulating a conversation between a student and our teacher model. So he asked the question, just a sec. Yeah, so here the persona of the student that we have chosen is a lazy and impatient student who doesn't want to solve the problem on his own and wants the solution directly. So as you can see, he's asked a question on lines and equations, which is a NCERT class 11 problem. And the student, Yeah, so the teacher has refrained from giving him the solution, and then it's encouraged him to solve it on his own and even given a clue so that he has some starting point. But our student is very adamant, and as he indicated it before, he doesn't want to solve it on his own. So he is asked the solution again. But then again, our teacher model, as expected, it won't give the solution. So it's saying you need to try to solve it on your own, and it gives an even bigger clue. How do you find the slope of the perpendicular line? So yeah, so now the student starts to solve the problem, but as you can clearly see, he doesn't know how to solve, doesn't know how to find the slope of the line, and he's basically begging for the solution. So that's where the teacher basically says that's fine. And then he says, he encourages the student by saying the goal of problem solving is not to get the answer, but to actually learn the concepts. So he teaches him how to find the slope of the line. And once you know the slope of the line and the point on the line, he asks him, can you find the equation of the line? So that's when the student is like, okay, fine. Just a sec. Yeah. So again, the student, yeah, so the student has still not mended his ways and still asking for the solution and asking it. Yeah, so the student still asks for the solution after giving a partial solution and asking the model to auto-complete it, but the model won't do that. It will give him the equation of the line and then ask him to substitute the values and find it on his own. That's it.
So as you have seen the demo, what we are doing is we are using a language model to teach the concepts to the students. So end of the day, since it is a model, it is probabilistic, it can hallucinate. So what we need to do is, for an educational domain, we need to mitigate the hallucinations that the teacher LLM gives. So here we propose a framework which contains 4 modules. Wherein the first module, when the user passes in the input prompt, it gets tokenized, and then it goes to the pipeline, wherein the pipeline monitors the hidden layers and observes if there is any representational drift, and then we compute the risk of the drift using HSIC score, and if that score is too high, we then use a judge LLM to classify if this is a reasoning based hallucination or a factuality based hallucination or a final answer correctness based hallucination. So based on that, we label it using 0, 1, and then the verifier comes into play, which iteratively refines, iteratively checks if there is any hallucination, and then based on that, the patcher pipeline comes into play, wherein it regenerates the response using better prompt or a RAG based pipeline. So the pipeline is as follows. As you can see, LLM generates a draft answer, and we check if that is a hallucinated response or not. And based on that, we go to the further modules. If it is hallucinating, then we regenerate it to get a better answer. So this framework is modular, and we have achieved better results on our data set generated. Yeah, that's it. Thank you.
So we are running out of time, so maybe we can take only one question. So any questions?
Thank you. This is Rajesh again. So that's a good job. My question is, are you guys planning to bring this to market? And if so, what are the courses that you're targeting?
Sir, for initial, just to bring our idea to life, we use K12. So we are soon expanding into ML and computer science, the software development.
Thank you.
One more question, if anyone.
Hi, this is Rajesh again, but this is Rajesh Haridas. So, first of all the best to your team. Keep going. So, my question is, what are your roadmap from a personalization perspective for, as a tutor, the important between a tutor and the student? Say, for example, how your lecturer thinks about how he should teach you and the last bencher, or someone who understand quick or who don't understand the basics. So there are a lot of things apart from your interaction based personalization. So any thoughts?
You're asking how are we incorporating personalization into our tutor?
Yeah, already or something in your future roadmap. Maybe you can think about.
Yeah,
If not,
sir. Currently what we're doing is in the Socratic LM part, so we're having multiple student profiles. As you can see, we showed a lazy student profile here. So we have multiple such profiles like class clown, joker and all this, and then a smart student, etc. So these profiles are inherently in our training data. So the model is able to respond accordingly depending on this one. For future work, we are planning to have like a user memory component where for each and every student, it is able to tailor its responses based on the conversation history and all that. So you have to finalize on an architectural decision. Once we do that, we'll include that. So,
okay, all the best. Maybe you can also think about characteristics of a student from various other parameters apart from the conversation.
Sure.
Wish you all the best.
Okay. Thank you, the MentorX team, for bringing your work to Casimel and contributing to this culture of innovation. Please, big round of applause for the students.